We often have a large reservoir that's filled with fluid, and it's often too heavy to lift, and sometimes we don't have a valve or a spigot that can help us get that fluid out. So the way we get this fluid out is by using a siphon. And a siphon really is just a tube that we connect into the reservoir and then connect to a lower elevation exhaust. But understanding what a siphon is, how we can get it to work, requires that we understand the hydrostatic equation. Siphons are ubiquitous. You can use siphons to clean your turtle tank. You can use siphons to get fluid out of your primary fermentation of your home brew and into your secondary fermentation. The toilet that you use every day is a siphon. And in fact, the way that the toilet works and the way a siphon works is what causes a toilet to sound the way it does, different from your sink or your drain. Siphons are also reliable and inexpensive. They are very effective at taking a steady input and leading to an unsteady output that has periodic bursts. This, for example, is used in men's bathrooms to make urinals flush periodically. It's also used in your basement hydroponic or aquaponic system to periodically fill and drain the tanks that the plants are growing. The hydrostatic equation describes the equilibrium of Z forces in a static fluid domain. If we look at this tank's filled with red-colored water, and the pressure inside this water varies from the top of the tank down to the bottom. We find that the pressure is actually higher than the bottom of the tank. And the reason for that is that equilibrium has to exist between two different forces. The gravitational force that's being applied to this water pulling it down, and the difference in pressure between the top of the tank and the bottom of the tank, which is pushing up and bouncing. We derive the hydrostatic equation by drawing a control volume and comparing the magnitudes of these different forces. A volumetric gravitational force that pulls down, and a pressure force that's a surface force that's applied all over the control surface. When these two are in equilibrium, the system can be motionless and can have an equilibrium of forces. When we do this analysis, the analysis is relatively straightforward, and the reason is because we have only two forces existing in the system. The pressure and the gravity are the only two things that we need to take into account, and therefore the only two things that end up in the equation. The final equation we get from this integral analysis is what we call the integral form of the hydrostatic equation that tells us the differences between properties at two different points in space. The hydrostatic equation explains how pressure varies from the surface of the Earth all the way up into outer space. It also explains how if you're scuba diving and you watch the bubbles as you release them out of your mouth and they rise towards the surface, those bubbles expand as they move toward the surface. In all of these cases, we can think of the pressure distribution in the atmosphere or underwater as being an expression of the magnitude of all the weight of all the fluid that is piled on top of the fluid we're considering. So if we have a reservoir that's filled with motionless fluid, there's a distribution of pressure vertically as we move along in different locations. The total weight of a column of water that's about 10 meters in height is approximately equal to the magnitude of atmospheric pressure. Here, we're about 1/3 of a meter in height. So the difference in pressure between the top of this water and the bottom of this water is about 1/30th of an atmosphere. So this pressure changes about 3% from the top to the bottom of the water. The pressure is also changing in the air above the water, but because the density of air is about 1,000 times smaller than the density of water, rather than changing by 3%, here it's changing by about 3 parts in 100,000. And usually that difference is a difference that we neglect when we perform a calculation on this sort of system. So a siphon essentially is just a tube that connects fluid at some high level to a lower elevation exhaust. And so if we put a tube into this bucket of water, we can use this tube as a siphon to pull the water out of this system. Now, as long as this water isn't moving, this water satisfies the hydrostatic equation. And that means if I hold this tube of water, we can see that the water has some pressure here at its height, which is equal to atmospheric pressure. As we move up in this tube from the surface of the water to where I hold my hand, the hydrostatic equation has to apply, which means that the sum of the pressure plus rho times g times z has to be uniform. As we're increasing the z-axis, we have more gravitational potential energy. As we decrease z, we have lower gravitational potential energy. Also, for the hydrostatic equation, as we increase the z elevation, we must be decreasing the pressure. So just as the pressure went up from this surface to the bottom, the pressure is going down as we move up this tube. If I were to lift this higher and higher and higher in the air, eventually I get to the point where the pressure is zero, or the pressure is close to zero, and this would cavitate. But that would be 10 meters in the air, and my arms aren't long enough. I know that because the pressure here is lower than atmospheric, if I let go of my thumb, the pressure of the air will push this fluid down. So that's not an effective siphon. But I can do the same math, and I can see what the hydrostatic equation tells me. And what it tells me is that if I hold it like this, the pressure here is lower. If I move it down and down and down, if I move the surface of this right even with the top, then I expect this pressure to be atmospheric. But as soon as I move this system down lower, now it has a lower Z value, which means that the pressure of the fluid must be higher than that of atmospheric. And that means that when I remove my thumb, that the water is going to come out. And this tube and this configuration, all it's doing is it's creating a connection from the reservoir to the exhaust. Because this siphon is filled with water throughout the whole system, the hydrostatic equation using the density of water is what applies. And this is a very simple way to remove, for example, the beer from one carboy and put it into another carboy, or to take the water out of your fish tank and exchange it. Now I can't do the same thing if I lift this up and I just hold it like this, because what's inside the tube is air. So the relevant hydrostatic equation calculation tells me that when I start at the surface of the water, I have atmospheric pressure. Now the pressure as I move up the tube is going down, but it's going down proportional to the gravity or the density of air, which is 1,000 times smaller. And then it is going down according to the density of air. There's no way for me to create a pressure difference that's going to drive fluid through this system, because I'm using height differences with air, which generate very large pressure differences, and I'm trying to use them to move water, which is 1,000 times denser. Again, I take the same system, and I just dunk the tube in the water so that it fills with water. Now I can uniformly apply the hydrostatic equation with the density of water, and that predicts that this density first, or that the pressure first goes down, and then goes up. Now the hydrostatic equation doesn't say how fast this fluid moves. In fact, as soon as the fluid is moving, all of our hydrostatic equation arguments are not complete, and they can't be used to describe the system. If I hold the system fixed with my thumb, the system's static, and the hydrostatic equation applies, it tells me that this pressure must be higher. As soon as I let it start moving, now I have to use the Bernoulli equation to describe how this fluid moves, and that's the topic of the video. Now, there are other types of siphons. We talked about a siphon that just had a tube that we either filled with water or didn't. When we filled it with water, it was effective at pulling water out of a reservoir. If we let it empty and it had only air, it wasn't effective in moving anything at all. If we could design a system that oscillates back and forth between these different states, then we can take something that has a steady input and create bursts in output. And this is used commonly in urinals and men's restrooms. This is commonly used in a variety of different hydroponic and aquaponic cultures to create systems that naturally fill and empty without having to use any active control system. And you can do that with what's called a bell siphon, and that's shown here. This is just a graduated cylinder, but inside there's a tube that starts here at the exit, loops up, and then loops down. And the reason why this is a convenient configuration is that this allows a system to oscillate back and forth between two different states. One state where the tubes in the middle are filled, and where the system acts like a siphon. But then periodically, it allows that system to empty out so that it doesn't work as a siphon. If we have a steady input through this tube, this system will periodically fill up and empty based on the operation of this siphon. Right now this system is filling. When it gets to the top, we'll effectively have completed the loop through the siphon, causing the system now to empty out. This fluid is now being pulled up and over through these central tubes, just the way I pulled fluid up and over with the tube on the side. However, when it gets to the bottom, that middle loop was broken again. Now the system fills up. Now this system doesn't have any moving parts, it doesn't have any valves to break, it doesn't have to be connected to electricity. So when the power goes out, this system continues to work. And this is one of the reasons why this is commonly used in hydroponic and aquaponic cultures, because you can have many, many different bell siphons like this, cost very little money, and it's very reliable. It's also used in urinal systems, again, for the same reason. You don't want to have to connect many, many valves using many, many sources of electricity with many, many opportunities for something to break. Again, all that's happening here is the same thing that I was doing with my hand. It's periodically creating a system where you have fluid filling a tube so that you have a siphon that works, and then oscillating that in between another situation where the tube empties and the siphon doesn't work. So, a siphon, at least knowing whether it'll work or whether it won't work, is a simple application of the hydrostatic equation. Anytime we look at static fluid in a reservoir or in a tube, the hydrostatic equation tells us that the pressure goes down as we move up in elevation and goes up as we move down in elevation. Regardless of where I move this tube, the hydrostatic equation always tells me what the pressure will be at the end of my thumb. And that tells me whether water will rush out or rush in when I take my thumb off. As long as I put the end of this tube below the level of this reservoir, I should be able to pull fluid out of this reservoir into this system. And again, this is now something I can do without a valve, without a spigot, or without a pump.